All right, let's get started. Welcome back. Good way we can do this despite striking. Of course, also its own motivations, but all hardware and recording seem to work. I want to continue with the rigid body simulations. And just as a reminder, I would like to pull up this slide again, because that's at the core of everything we discussed last week, basically. Any questions or comments here about this part? That's definitely going to keep us busy for the remainder of today's lecture. I hope the main idea is clear. In a way, we're doing a simple Euler step here for two quantities, just like before, right? We have accelerations for velocity, from velocity to position, main change being the one at the top, and these two, the angular components that we have now in our equations of motion. So, you can still think about topics to discuss. One thing that I want to explain in a bit more detail today, we kind of left off and that I just dropped onto you, were these equations here. The impulse, I remember, so that's our motivation for basically, I brought my not so rigid bodies again, right? We're dealing with rigid objects, but in reality they're all deformed, and handling this deformation and the response in an accurate way, that's actually really physically accurate for the idealized model of a non-deforming body, is handled with these equations that look a bit scary at first, admittedly, especially here all the terms at the bottom. But I now want to explain where this comes from, to give a bit of background and to make clear that this is true, right? That's in a way the whole idea with math. We go through the steps to show you can really derive one from the other. It directly follows. So these equations were also important, going to come up in various forms in the following, but I hope you remember. So we have these impulses. So here this is the top is the whole one, the bottom the linear one to get started. But here we have the J, only the linear one for now, and it basically works a bit like a force, if you want. Right, so we had J being scalar along the normal, we have a direction. But to let that act onto one of our bodies, we actually need to divide by the mass, in line with Newton's second law, to get a change in velocity, and most importantly, no time step here. Right? Euler integration also would have time. This is instantaneous. We really get that whole change, as motivated a bit last time, in one go. We assume basically our model here is this happens at an infinitely short amount of time. We're changing the velocity. This is for body A, and for body B we have basically the same, but if you remember, we don't want to create energy out of nowhere or so. The impulse preserves, especially momentum, and it acts by definition, just how we basically set up our coordinate system, in a positive way on A and in a negative way on B. So main idea here being, we don't want to change the whole momentum. We add something to one, subtract it from the other. Then overall, we keep the same. Does this make sense? Yes, that's the question. So. Exactly.
Because when I was doing the exercise with the tutorial last week, they took the VA was not that you computed velocity from A, when was the velocity of center of mass that we started?
Sorry, so this is, you're right, this is the center of mass velocity. This is the linear part, right? The center of mass of our rigid bodies moves like a particle. Just it doesn't know about rotations or so. The center of mass just moves along with this velocity, yes.
We had to also compute a velocity in our tutorial at the beginning. The formula would have been rather helpful if it was
Exactly, this is not the collision point. Oh, you're saying in the Tutorübung it was not clear, or we should have distinguished here that this is center of mass. Okay, okay, thanks for pointing this out. Right, it would unfortunately add to the whole derivation, but it's good to point this out. I'll think about it. I think it would blow up all the equations a lot if we each time wrote basically Cm dot comma A, Cm comma B or so. But all these quantities are center of mass. There is, later on, we'll have what we typically in this equation call xc, the collision point. But it's good to distinguish. These are assumed to work on the center of mass. Well, you're talking about, okay, yeah. Might even be worth another drawing again. So we have our bodies, right? So, and just draw it out again, right? So we have two center of mass locations. These we typically called center of mass. And now we're dealing with a collision point. In world space, similar to the center of masses, this is called xc. But for the two bodies, these are relative locations on the body, right? So it's also important to note we have two vectors here, xa and xb. We have a lowercase b, right? Like this, which we already have up here actually, right? But these are relative to the center of mass. In a way, so for these equations, actually, it's how the center of mass moves, but yeah, it's this velocity is associated with the whole rigid body, and we typically assume it acts on the center, located as center of mass, but really it applies to the whole body, of course. Yeah. Yeah. So for the relative velocity, okay. Yeah. So that's also a good point. We are coming back to the relative velocity, and the relative velocity is actually the one at the collision point. You're right. These two velocities we typically associate with the center of mass, but the relative velocity which you already have up there, that's the one right at the collision point. It actually can happen due to some rotation that it would look like the bodies are colliding in terms of their center of mass. I have not drawn any velocities here, but right, it could happen. But the bodies are spinning so quickly that at some point outside they're actually going apart, right? So even if you would compute a relative velocity at the center of mass, and it might look like this is negative and colliding, the actual collision point might do something different, right? The angular velocity could overrule that basically. But okay, it's a good point to keep in mind whether we can make that clearer to distinguish between center of mass values and collision values. And on a high level, most of what's happening here is actually at the collision point, right? The relative velocity and all these changes, I'll come back to that in a moment. All these terms act on exactly the spot. It's just the overall linear velocity that we're updating, we're changing it, but that's at the center of the bodies. So you can basically think about this collision happening at this location changes, right? How the whole body moves and also how the center of mass of these bodies moves. I think it doesn't hurt to go into some of the details here once in a while. And yeah, so one important point I wanted to make here is this plus and minus, right? So we basically have a sign change here. All right, let's get started. So I want to focus on the linear impulse for now. We have a relative velocity, as just mentioned. So this is now This is a general relative velocity, but we actually need this. So here this is already, right, this is general but potentially misleading. So we need this at the collision point. This is what in the end makes a difference. Here should primarily indicate relative velocity is defined as a minus b. And that's part of our coordinate system for the collision. You could compute the relative velocity of anything. Typically, we need the one at the collision point. And then we have two important quantities, namely the velocity before the collision and then the correct updated one after the collision. Right. This one should be negative going into each other, and this one should fix this in a physically accurate manner. And this is exactly now where this coefficient of restitution comes in. I hope you remember, that's our C here. That describes all these potentially very complex effects from deformation and how mass is even dissipated due to plasticity. So this actually captures a lot of things, but you can measure it or model it. And it basically tells us the velocity afterwards here should be positive in our coordinate system, meaning separate the rigid bodies and reflect whether for 0 here we have something plastic, or for 1 we have perfect bounce back, or anything in between, right? It can be between 0 and 1. But no other values allowed. What would happen for value smaller or larger 1? It would violate the conservation of momentum in this case, especially. That's correct. And also, if you think about it, if it's less than 1, we basically don't even remove the negative part. That would mean we have a collision, but the bodies still continue into each other. That cannot be. And if it's something larger than 1, that would mean for basically 1, we get a perfect bounce back. Overall, in this case, also conservation of energies. If it's larger, then we actually create something. Then the objects would accelerate from the collision. They would create something out of nowhere, basically just from colliding, which could potentially happen with something like an explosion also happening at this point, right? Some additional effects. But if we just look at not deforming passive bodies, right, that should not happen. So larger than 1 is also not physical. Less than 1, actually, as mentioned, would dissipate and remove energy. All right. One important change for the whole calculations that we're doing is we're considering this just along one line, as mentioned before, typically defined on the surface of one of the bodies, just considering all the values along this imaginary ray shooting through our two bodies. Turns out it's enough. And it simplifies the rest a lot, because as you already saw, the equation is not super trivial. And if we would need to do this for 3 components, potentially coupled, well, it would potentially lead to something like a 9-fold increase. And hence, as you show, all the physics are correct if we just consider a single value along this normal direction. But this equation now already took 2 steps. So here that we have a relative post-collision velocity, we already inserted a minus b here, and then project this onto the normal direction. And on the right side here, we just compute a dot product, project the relative pre-collision velocity also along the normal direction. So the reason why I'm not writing this out, of course, you could also write a minus b here, but this is all known. This is basically something you can pre-compute. We exactly have this VR. Yeah, that's our state before. That's the bad part. That's the negative one. And hence, also in practice, you typically just compute this. All right. So this is now an important starting point, this equation here, because basically if we take this one and how the impulse acts, this is exactly the equation I had on the slides just now, right? Plus minus j for the two bodies. This is basically all that's necessary, and that gives us the other equation. In a way, that's it, but it's not so obvious. So let me write it out. But please keep in mind, this is already the crucial step. So I hope this one here, equation 3, that's clear. Makes sense? Relative velocity at a minus b, and we just multiply it by c, and then look at it along the normal direction. So in a way, I would argue it's pretty simple. Now we just need to insert how these two were computed, right? So these two values we don't know yet. That's the post-collision velocity, right? This is in a way what we're looking for. We don't know exactly how they're, the values, what they're like, but we know that these equations hold. And I'm just seeing that these equations have a typo. So these dashes here shouldn't be. I think you can erase this here. Right, so this is. No, sorry. Of course, this is. Okay, I'm getting confused here. This is correct, of course, right? This is, again, the velocity after. This is the one before, which differs just by the impulse. So, all good. No, it's correct. These equations for the linear impulse now tell us what the velocities look like, here how they're constructed, and this we now use here to compute j. Right, so these exact values we don't have. We're actually looking for j, and we know afterwards this is how the post-collision velocity is affected by the impulse. So we're still looking for how do we actually need to compute j. This is our task here, and we know the relationship in equation 3 holds. So basically what we do now is we'll take this part, insert it, this part, insert it into A here, and then resolve for J. In a way, that's all. So here it's written out exactly this insertion, right? So here we have A, here we have B. Mind you, already used the negative sign here, right? So we have minus and plus. Oh, it's clear, right? It's just an insertion. Just put these two into equation 3. Just to recap again, same from the previous slide. Now we need to rearrange this a bit, and I've written that out here a bit. So again, we're looking for J up here. This is what we want to get out, so we'd like to separate it. One thing we can do here is first you can up here rearrange. So here we have A minus B. I hope you can see that. That's our relative velocity. So you can imagine basically writing here VR plus these two. And then we have VR. We can bring it to the other side. We already have VR here. So we do minus. We get an additional -1 here. That's where the 1 plus comes from. It looks weird to just add 1 on the right-hand side here, but it's right. In a way, we already have the relative velocity on the left-hand side here that we pull out, bring over. And then we are left with these two terms. Here we pull out the j up front, and then also the multiplication by the normal we pull to the back here. And now this term here is a dot product of two normals. They're both normalized. Projecting one normal onto the other gives two vectors with length 1, dot product, gives you 1 again, right? So this is 1, or basically it just drops out. And I think, well, I don't have another step in between, but right, so this drops out. And then we can just bring these two over. And we already end up with this main equation for the linear part. Right, so here that's written in one line, but it's 1 over mass A, 1 plus 1 over mass B. That's here what we divide by, and this is just the part here on the right-hand side. Does that make sense? So the main thing is really just we're saying, well, post-collision velocity is minus c times the old one, and then we insert how we compute the velocity at that point. So this is a linear part. That still looks nice. We also had it on slide as a starting point. Because as you remember, also a discussion, I hope, for the center of mass actually doesn't matter where the collision happens. That was this question we had discussed the last time. It's first sight a bit unintuitive, but it doesn't matter at all whether my two bodies collide right at a corner and start wildly spinning, or whether I have something happening right through the center of mass axis, right? The center of mass quantities are always influenced, and they can't end up in the same way. If I just look at single forces, this basically, the center of mass is independent of where something happens. As long as I have a change, namely that change by the impulse here, and it's already a bit hidden, but right, for example, this change does affect the center of mass, irrespective of location. For angular velocity, the position plays a larger role. So, but it's exactly the same idea. Only now computing these velocities at the collision point is a bit more complicated. So here it's written out. This is exactly what we had before. New are these parts for the angular velocities. This admittedly looks a bit weird at first, but the idea is you can kind of read it inside out. And it really, in a way, just tells you, well, how does the impulse that we still have to compute, that's happening somewhere, influence the collision? Actually, just the velocity. In a way, it doesn't even matter where the impulse is coming from, but just this velocity at the collision point. But potentially, this would hold for any change of velocity at the location of rigid body A, for example. So what we have here is first our impulse here. Right, this is just, again, J. Now, J indicates the whole one, linear plus angular, at along the normal direction. And if you think back about how we had forces working on our rigid bodies, this is basically like a torque, right? This angular force that was defined as the relative vector, this xa here, cross our force vector. Now we have this impulse. But that part basically tells us how does the torque, or what kind of torque are we getting out of this impulse, out of this instantaneous change. And I hope you remember, torque changes which quantity? Or does anyone remember? It's actually not, it's not so obvious, but similar to before. Actually, this is like a force. It doesn't directly add a change of velocity, but this changes the momentum. In this case, the angular momentum. Right? We had this capital L. We had these torque values to change the L. Likewise, here, if we only would look at this, we'd have a change of angular momentum. Here, we really need a velocity. It's not a good idea to try this with momentum. We need the actual velocity in our collision point. Hence, momentum is mass times velocity. We need to divide by the mass. And the mass for these angular components is its inertia tensor. That's what this multiplication is doing. So momentum times divided by the inertia tensor, written in terms of an inverse, -1 here, gives us a velocity, angular velocity. Right? We're all dealing with rotations. But this inner part here, you can basically see as a delta W. This is a change of velocity. That's why now it's actually fine to add this to the other w, right? If we would have a different quantity, this would be physically not allowed. This way now it's correct. We have one velocity plus a change in velocity, giving us a new angular velocity. But I hope you also remember our angular velocities always work in this inconvenient way of being perpendicular to some axis of rotation. So to find out how does a point now on our body move because of that angular velocity, we need to transform it back to that point. And that's where we get this last part from. You also remember, so I just write it out, we had equations of the form angular velocity cross some vector x. This gives a velocity. And that's exactly what we have here. Right? The first part is angular velocity w cross x. So I hope if you read it from inside out, you get this whole, in this case, really a world space velocity that we could call v, or the instantaneous velocity at that point, from this change of angular velocity. Just like before, for the linear part, just a bit more complicated because these rotations are actually not so easy. Does it make sense? And now we just have to do the same thing again. Unfortunately, now this is getting a bit longer, but we just insert these two into the other equation for the relative velocity. Exactly, into this one, I hope you remember. And then we rearrange our equations. And yeah, this is where things get a bit ugly, because now we have a fairly long list of terms here. But it's really just insert, right? So this part here goes, okay, slightly split here, and this part here gives us b and this term over there. So it looks long, but in a way nothing complicated. And now we basically have to do the same as before. We need to rearrange this, and we are still interested in what we want to get out is this j, right? All these we somehow need to extract and then solve for j. And luckily, actually, it looks complicated, but it's possible. We can just pull it out and get an expression for j. Now, one thing, actually, just like before, in here we have the relative velocity. We basically have one in these terms. We have 1 VR. Now we have the full one, not just the linear one. And this also comes from these WA, WB terms. These four, together with these, make up our basically, it's essentially -1 globally here on the right-hand side. So later on, just like before, here we had a 1 plus relative velocity again on the right-hand side. So that removes some of the parts, but what it leaves us with are a few others, namely these inner terms. These stay. I mean, that's basically how the impulse acts, right? That needs to stay on the, for now, on the left-hand side. Yeah, but unfortunately, they don't simplify much. So in 3D, we're actually keeping most of this. I'll show it in a moment. Right? You can take a look at these terms up here. That's what we get for dividing by in a moment. In 2D, I gave you a slightly different equation, slightly simplified one. It's nonetheless, I think, not a bad idea. You sometimes see this one. That's possible because in 2D, the inertia tensor, which we have here and here, for turning our momentum into a velocity, in 2D, those are scalar. Right? Remember, in 2D, we only have one axis of rotation. 3D, this is a tensor, or basically a matrix 3 by 3. But in 2D, because of that one axis, our plane, right, we just rotate everything in some plane, the screen or so. These two i's are single numbers, or it's basically an inverse. It's 1 over, we sometimes wrote it as this lowercase I. And this number we can pull out. Later on it's a matrix, then it's not possible anymore. But if we can pull this out, then there's a nice simplification you can make. Just rearranging, you can show that for vector notation, this expression can be turned into this cross product squared. That is also basically, we can look it up. It's just a vector identity. I hope you believe me. We could write it out, but right, this holds true. Basically, for cross products and dot products, right, we basically get this one squared, which does not work if we cannot pull out this factor here. And with this in mind, in 2D, what it looks like is right, basically this position cross normal squared. We have this term for both A and B. It looks slightly nicer than this up here. And this is what you typically find for 2D impulse equations. But 2D, this is now the whole expression containing these four terms, the two linear ones and the two angular ones. Yeah, and for completeness, in 3D, unfortunately, we need to keep everything. This is the equation we'll have in 3D later on. Just write it out. It also directly follows from this, just not simplified, basically. Yes, there's a question. Mm-hmm. Exactly the position squared, basically. All right. We come to the 3D version in a moment also. In 2D, right, it was just basically mass times the position of some point, right? So this is a vector squared or dot by itself, right? So basically dot xi again, right? And this is basically, this is squared distance, right? That tells you basically how far away something or this vector x is, and we always had x from the center of mass, right? So we have the center of mass location, and then our xi at any point here could be this one. So this is a squared distance times mass, and this accumulated for all points in your body. Actually, for a real body, what you should do is an integral. It's continuous, but with point samples, it's a bit easier to think about it. This is the inertia tensor. You can show that this is the equivalent of a normal mass, the whole mass of the body, but this is how this mass acts about 4 rotations of this body around the center of mass. The capital I? That is exactly 1 over this quantity. Here this is the form you can find in higher dimensions. So potentially this would hold in more than 2. And then it's actually a tensor with a number of, so it's basically a matrix. Exactly. It's just 1 over. In general form, this dimension here, this depends on the number of axes of rotation you have. So in 2D we have 1, 3D 3. Other systems you might have more. Right, so basically the number of entries you have here is determined by the number of axes. And in 2D, you can basically still think of it as a 1 by 1 matrix, but it's a single number, and the inverse of a rank 2 tensor or a matrix 1 by 1 is basically just 1 over that number here. So that's why we can make these simplifications. I think it's a bit easier to think about in 2D basically, but this formulation holds also for more dimensions. But also from intuition, what I think is important to keep in mind, it's basically we're dividing by the mass. It's still a division by mass, just how the mass acts for rotation, right? For things that turn instead of linear translations. All right, yeah. Good, we captured this. This is also, I can promise, the most complicated equation we'll have for a while. But right, there is actually some intuition here. It looks bad on first sight, but I hope also now with this derivation, you kind of know where it's coming from. Yeah, that concludes this whole part. What I now want to continue with is moving to 3D. And for that, we need to look at a different topic, namely orientations. So in 2D, it's really, or these orientations are actually in a way surprisingly complicated. Also, our brains are not very good at processing rotations. In 2D, in a plane, we just have this one axis. It's pretty easy. But in 3D, we suddenly get two more. Right? It's not like position. Position changes from 2 coordinates only by 50%. It's just a bit more, but it's most of the same. For this linear part, 2D, 3D is almost the same, but rotations really fundamentally change from 1 to 3. It's 3 times as complicated. And this is what we need to deal with now. And also to look ahead, there's no simple solution, unfortunately. It's really not that easy. But hopefully this is going to make sense later on, nonetheless. So because there are some difficulties, actually I want to, again, restart a bit and motivate this. Such that you understand a bit, instead of just dropping the final result, where this is coming from, the complexity we introduce here. But because, right, you can download slides. If you look at the back, the final solution basically is not that intuitive, but it has a reason. All these orientations and rotations that we're dealing with basically are transformations. So we need to deal with coordinate systems. Right? Imagine we have 2 or 3-dimensional coordinate systems, pretty old topic. Imagine, right, holding your hand out and defining these. You need it for rendering. So this is a super old picture from rendering, where you also always kind of need to deal when you want to simulate, kind of show what's in a virtual world. You need to have a world coordinate system. You typically have some for objects, a bit like our rigid bodies. You want to position some object, then you have a local coordinate system. You can define these differently. And one fundamental change, for example, is if we have any coordinate system, you can span it with vectors that are basically made up from your right hand or from your left hand, and you cannot easily transfer one into the other, right? So if I try to align these two, I hope you can see a bit, but basically my thumb points in the other direction. Basically one axis is flipped, right? I would need to bend my thumb over back, which I won't do now, to get this coordinate system. So there's inherent flip for your thumb axis, which in this case is the x. So that's, for example, one fundamental change you need to make. Both span the same 3D space, but right, we can, for example, flip an axis, something you cannot easily account for with a rotation. That's left and right-handedness, which you basically find in any API, for example, as something very fundamental that needs to be baked into all the following calculations. This is typically introduced in terms of affine transformations. Maybe some of you still remember that from the imaging or rendering classes. So what we do for projecting something onto screen is introduce these affine transformations for a world. And the reason why I'm bringing this back is, right, you might think, well, we're dealing with something very similar, right? Instead of putting such an object onto a screen, which typically works by finding it somewhere, then putting it into a world, rotating it in the right way, and then projecting it back onto a screen, right? You're flattening it out in the end. This is what we do for showing something. Well, now we're trying to track it in 3D, but it's not so different. So, well, why not use this? These affine transformations have a few inherent properties. Right, so, for example, that parallel lines stay parallel. A couple of things can change, angles and length, and, for example, this handedness of a coordinate system. But You can do quite a few different things with it, and this is typically how these affine transformations are expressed. So here the X is now not a single number, but entries. So we have a matrix that basically has these 3x4 entries. I hope you remember a bit. This part is something that can actually do all the shearing and rotating. And here we have another part that would potentially also account for offset and also for the projections later on. The homogeneous part. But right, if you think back about what you typically do to get something shown on screen, in a way we have a tool here that would rotate and actually do even more than just rotating. It would also mirror or shear your objects potentially with these 9 entries. And I think I do have this on the slide. Right, these entries potentially are there to just move around things. Now, and 2D rotations are also pretty simple. If we want to define a matrix, say that 3x3 part of the previous matrix for 2D now, gives us a 2x2 matrix. We have single axis of rotation, namely the one poking out of or in to your screen. If you want to rotate by a vector phi, you can show this is what you need to multiply with. So some rotated location P dash gets as input the previous one, and if we multiply by a matrix R phi of this form, we get the rotated coordinates. But that's basically, you can imagine this basically spans a circle. We have a vector here to define 2 vectors which are exactly spanned by these 2 columns and also rows, right? And you get a rotation from here to here. In the matrix, we have basically normalized vectors doing this. Then if you multiply it with some other vector, right, you can basically transform any other vector by this amount. Right, so here we have these entries. It's basically set up in terms of orthonormal vectors in this transformation matrix. This also holds in 3D, and if we look at rotations on a single axis, it actually stays pretty simple. If we rotate around a single axis, right, so in 3D, with 3 ways to rotate, right, the one we had before in screen, then we can use one perpendicular where it's rotating in and out, and then we also have one poking through it from the top, so 3 possibilities. But if we restrict ourselves to these Cartesian axes that our coordinate system is already basically built of, then the process stays very similar. Then we can essentially use a 2D rotation just acting on the parts, on the perpendicular components. So here is one example where we can pretty much take the same coefficients as before. We just look at now a rotation around x. So x is kept. In this case, a bit like before, I hope you remember, if we basically rotate something around a center in our plane of rotation, so it's easy to show again in this 2D plane, but for example, the center of our object, right, it doesn't move. So this component actually should not be modified by our rotation, but everything around it potentially can. So we're looking at a plane now that rotates y and z axis. All right, so this is y and z, and those get modified by the same coefficients. And you can basically repeat this for y and z. We can set up these rotation matrices x, y, and z to rotate around any of the 3 coordinate axes by a very straightforward adaptation of these ideas. So right, let me quickly finish this topic. Here we have rotations on single axis. We can basically combine them. Right, you could imagine if we want to rotate around some other axis, we could combine a few of these, do one after the other, and just multiply multiple of these R matrices. However, you can actually show, instead of setting up separate matrices and multiplying them together, you can directly combine that into one expression to construct a matrix. And this is now a generic rotation matrix that rotates around any axis given by this vector a, ax, az, ay, az, by an angle phi as before. And it's actually very similar. We have a lot of cosine and sine terms by phi, cosine phi, sine phi, just combined in exactly this way. So there's more, you can set this up. So basically, if I would want to rotate around any axis by a certain amount, I could just use this to set up one rotation matrix that, again, if I now would write r times some vector p, would give me a rotated position p dash rotated by exactly this amount. Right. So in 3D, it's actually good to keep in mind any rotation matrix like this is actually still built from column vectors. So you can think of the matrix we get out from the previous slide as basically constructing a little coordinate system. It's like setting up three vectors, x, y, z, that rotate out three axes. So we have one vector rx for a column here, ry, and rz. Those take the previous magnitudes along that axis, the entries we have in our point, px. This was basically how much some 3D point is moved along the x-axis, right? And this length we have here along x, this gets rotated onto, in this image, this rx vector, right? So this part here ends up in the spot defined by rx, this direction with the current length. It's basically scaled, right? If there was nothing, it's also 0 now, but if I had a 10 here, I would get 10 times the rx. The same happens for y and z. So in a way, these rotation matrices actually have a lot of intuition. They're built from these orthonormal vectors and just rotate your whole coordinate system. So one big question here is, well, I have these rotation matrices. I can set them up for any angle. Isn't this what we want or need later on for our rigid bodies, right? We could then just take any point, multiply it with something like this, and get our final orientation. This seems like a good starting point. It's not. You can imagine if I'm presenting it this way, we will not use this later on, but I think it's important thing to think about, and this motivates the alternatives, why this is actually not a good idea. Why it's not a good idea, I want to discuss in a moment after a break. So let's meet again in 5 minutes to look into this. Let me start a timer. All right, let's continue. There were two and a half questions here. Quickly repeat for everybody. So for the exercises, we will publish a reference solution, so you know what was wrong, right? We won't go through your source code in detail and correct bugs. Unfortunately, we don't have the resources for that, but you will get a reference solution. And please start with exercise 2 as soon as you can. This is actually one of the tougher ones, and it's completely independent. You won't need any of your mass spring simulation code for the second one. It's the same framework, but it's a completely new simulator. So you can start right away. You don't need any part of it. All right, and then another question was about the collision points. So yeah, please keep in mind, I don't have it on the slides anymore. I remove this. But we have different coordinate systems, right? So typically the center of mass is in world space. It's where our object is with respect to some coordinate system in the corner or so, right? The center of mass location. But all the x we have for the collisions, this xc, also the xa and b are, sorry, no, xa and xb are actually local relative to the center of mass of a body. This xc for the collisions is typically the world space location of that collision point. There are multiple, unfortunately, we have different coordinate systems here. So please keep in mind which one is the right one. And for a rigid body, to compute quantities of a rigid body for angular components, you always need the local ones, right? So for updating any W value, you need to know where something acted on your body. And it's, especially in the exam, it's actually easy to forget that and take a world space quantity and put it in your equations, and suddenly you have, right, something spinning super fast because it's the wrong vector. So please keep in mind basically which I would recommend to think about it in terms of a coordinate system. Are you in rigid body space or in world space? We had these rotation matrices. Here are a few more aspects of what they do or how they're built. Right, one mathematical quantity that makes them kind of interesting, and actually they also pop up in all kinds of other contexts. They're formed by these vectors that are normalized and orthogonal to each other. It's an orthonormal matrix, which means you can show for an orthonormal matrix the inverse is actually the transpose. It's actually sometimes super useful if you want to invert a even potentially large orthonormal matrix. You just need to take the transpose, which is very cheap. Intuitively, it means if you apply this matrix that nothing gets lost. That's why it's so simple. It just rotates something, and to basically undo that, the inverse of a matrix undoes what the matrix did. You want to rotate back, and that is what the transpose does. So rotation matrix, we typically multiply on the left side, rotates by a certain angle, and then the transpose does rotation on the same axis by minus that angle. So they do actually have useful properties, and even in spaces that you cannot really imagine, these rotations do come up. Yeah, so but the handedness you actually cannot change. Also the points on the axis of rotation don't change, because that's what you're rotating about. But right, why don't we use it? So one thing to point out again at this point, so now we have a rotation matrix that just rotates a point into a new location, and it's important to distinguish again. So we typically have a rest pose, say for this head here, as it nicely, it's obvious which direction it points to. And then this body has a new current orientation, but please don't call this rotation. So we basically, to get there, we apply a rotation, right? So we take our head and rotate it to get some orientation. This is an operation we'll have a lot, but what we're talking about now, right, the rotation matrix is coming basically in here. They do this. They give us this result based on some, you would often call it rest pose. Yeah. I will now talk about a bunch of different solutions that we can use to perform the step in a simulator. Here's an overview. It will be called fixed angles, Euler angles, with details to follow in a moment. Quaternions, which is what we go for, And then these rotation matrices as a more general concept. Let's first look at these fixed angles. So the idea here is actually based on what I had on the slides before, right? We have, in a way, the simplest starting point where these three axes and rotations around our three axes, x, y, z. Maybe not the most efficient way, but they're pretty easy to set up. Why not use that? So we need to define some order. It actually doesn't matter which one you define, that's mathematically equivalent. But we could say, well, we first rotate by x, by y, and then by z. That's our final answer. You could also say, well, first y, then z, then x. That doesn't matter. As long as you don't take a single axis multiple times, just any permutation of these three would actually be fine and leads to the same answer. Then we construct our rotation matrices for that. So remember, multiply it on the left-hand side, so r times point. To get the final one for some order x, y, z, we basically construct these three. First multiply by r, then by y, then by z. Right, so you could basically just multiply this with a point, and then effectively you would first rotate it around x, around y, around z, to give you some rotated point that we call p dash. In a way this works, right? So we can actually express any target rotation by this. There's a variant here that that you can also do what's typically called Euler angles. You could say, well, isn't it more useful if I don't rotate around, right, my world coordinate system, say this room, but instead I look at my rigid body and say, well, I define these local, right? So especially if you think about it as a box, I actually have three axes here for my object, and now I define changes of orientation by rotations around this local coordinate. So for example, around this axis, right, this of my body and the central one. And it also gets me everywhere. And now it's a bit more aligned with our rigid body viewpoint, right? Remember, we later on know there's an object that doesn't change, flies around, and rotates. So we have already, in a way, quantities for the body. Why not express changes local to the body? It's another alternative. And it's actually pretty popular, say, for planes. If you're sitting in a plane, you don't want to deal with the world space that potentially things are pointing backwards or in other directions. You just think about, right, this is my view of the world. It's relative to me. That's typically actually called differently. You have a so-called heading, which is defined as a z-axis. That's this one up and down here. That's basically the global orientation, left or right. Then you have rolling around y, typically defined. So this is really like rolling your wings left and right. And then the last one is the pitch, typically defined x along the plane. So this goes up and down. So this is actually, it's in use. It's a valid alternative. And interestingly, it's almost the same as the Euler angles, because if we now again think about doing this for local x, y, and z axis of our object, do we actually call these differently? So typically we apply some dashes here. So we say, we want to rotate by some z, some x dash, and a new y axis. And if we now set up a rotation, say around this local y axis, then the local y axis of my body here, right, no matter where we define it, maybe it's this one, is actually the one where we first undo the other two. So we basically rotate back along this direction to get back to a normal world-aligned y-axis. Then we rotate, and then we transform back. So if we want to do something like this, we actually basically, remember, we always start on the right-hand side. We first undo the rotation by the current rotation that we have of our object by z. So let's call this, let's call it the inverse to indicate that this is undoing it. And then we undo the one by this x-axis that we had before from the z rotation. It's also being undone. Now we can rotate by y. And we call it by y dash, but now y is aligned. So y is actually the same as world space y. Now we're not in body space. We have done some rotation on y, but now we need to get back. So now we actually need to rotate by x dash and by rz again. So we get this whole batch of first undoing things, rotating, and then going back. And now if we do the same thing for our x dash, we actually still going from right to left. For x, we now again need to undo z, rotate by our x. This is now actually coming back to, again, a world space x. And then apply z again. And now I think I switched the order here. Because what we should be getting out is actually a reversion, a reverse of these terms. So if we actually do this before applying this rotation around y, sorry, let me write it out. So same terms as before, just now written here up front. And then you get these terms. So now you can see that this RZ cancels out, right? We have RZ times R inverse, rotate back and forth. Then here for the X, we rotate here initially back and then undo this. So we left, for this lower expression, we actually left with the RZ. And if we then multiply this whole thing as a last component with the rotation on Z, oh sorry, we had a dash here. So it's another addition after this one, just giving us a rotation by Z, which again cancels out. We actually left with these terms. This also was, so, which basically means to apply body space rotations, you kind of need to flip the order of these rotation matrices. And so if we now in body space go from Y to Z, you're basically flipping the order of the matrices, how they're applied compared to world space. So the main difference from before, sorry, I need to get rid of the pictures here. For the Euler angles, we have for rotation XYZ, we get rotation matrices ZYX. And for the body coordinate systems, we get this flipped. For body space rotation ZXY, we also get rotation matrices that follow the same order, ZXY. So that's the main change. The flip in the order in which we apply these rotation matrices. So it's basically just flipped. long story short, so we can actually use both. They both do the same thing. Just keep in mind which order you apply these individual matrices. The problem is that both of these have problems. They're both not unique. So one way to think about this is if we have an object, and this is now making one example. So this object is actually not a good one because we also would need some more features along along 2 dimensions. So here it's actually done for an R, but the case or what should be happening here is we basically should be rotating some object here around some coordinate system down this way. Right, so I basically want to make this flip of my object. In this case, specified as a 180-degree flip around the x-axis. I can actually get the same answer in a very different way. I can first, this doesn't matter so much for this object, but I can flip it around and then rotate around this z-axis in this example. Right, so can you see it from the images down there, right? So basically this flip is the same as this. Might not seem so bad. Well, both are giving me the right answer, right? It's both a correct orientation in this final spot here. But if you think about it from a simulation and dynamics perspective, to get to one answer, I basically have 2 very different ways of expressing the same target state. So in terms of math, if I want to reach that state, it's actually not clear which solution I should get. Both are absolutely correct, but it's more than one. It's not unique. If I try to solve for this, that means I have an underdetermined system. It's basically not clear which solution I want to get. That's one problem, a lack of uniqueness. And then maybe even worse, this is a bit tricky to visualize. Unfortunately, it would be great to have one of these gimbals. They're called these Aufhängung. But I hope this image shows it a bit. If I rotate the wrong way, what actually happens is I remove a degree of freedom. Right? So here in this normal structure, you can see we have basically 3 axes of rotation here. One is this one here, and this one. So all 3, I can rotate in all directions. If I rotate this device such that the inner part, the silver one here, aligns with the outer one, the blue one, suddenly both of the axes of rotation are aligned. In this image, they're both rotating around the up and down axis, which means in this configuration, after this kind of spin happened, if I end up in the state, I cannot rotate anymore around this 3rd dimension here. I've lost an axis of rotation. I've lost degrees of freedom. And this is bad. Right, so if I do such a local coordinate system, or it can also happen in a global one, but basically the 3 different angles, I might end up in a state where rotations around the 3rd part, any of the 3 actually, but think of it as a 3rd axis of rotation, just don't do anything anymore. Right? If I'm in this state, I actually cannot rotate my object around this axis, and that's bad because we're dealing with physics, right? This may never happen. Now, physics might require us to rotate here. We have a collision from the side, so we absolutely need to avoid this. We would have such a state where object cannot move in certain ways that would break our simulation. Right? This would be absolute no-go. Interestingly, this is actually a problem. I think in the 50s or 60s, even NASA tried to navigate spaceships, or actually aerodynamics agencies tried to navigate with these, and they had complicated procedures to assure that you would never get into a situation where you would lose these degrees of freedom. So this is really, even NASA was fighting with this at some point. I think by now they actually also switched to other representations that we come to in a moment, but this really was a fundamental problem back then. And we don't want weird if statements or so in our implementations. There's a much nicer mathematical way to inherently handle that this cannot happen. Yeah, so one other talk about bad things that can happen. We could also not use these three different angles, right? So what we had before, or the implicit approach was, well, let's use three numbers by x, y, and z, rotations, to express some orientation of our body. Another question you might, or approach you might come up with is, well, let's use the whole rotation matrix, right? These 3 by 3 entries that we have in a rotation matrix, and work with that. As shown before, that actually also gives us any state. Mathematically, we can rotate into any desired position. The somewhat unintuitive thing there would be, right, before we basically had three angles. You could call them phi x, phi y, and phi z or so. So three values to track for rotations on x, y, z. If we use a whole matrix, we have a whole matrix, meaning we have 9 values. And we basically need to track all of these 9 and update them. So it's 3 times more, and it's actually too many. So what's the problem is, if you do this, as you can show over time, if you track a whole rotation matrix, they can actually drift a bit. So it can end up not being a real rotation anymore. Which is bad, because then suddenly your rotation matrix, which should just rotate things, might end up stretching or deforming your object in weird ways. So this is something we definitely don't want. Then it's not a rigid body anymore. And in a way, it's wasteful. We have those 3 angles that we know should be enough. Suddenly we have 9 values, so it's not so nice. You can actually, to some extent, fix this by a reorthonormalization, kind of like a Gram-Schmidt process. But yeah, it actually is not the best or not the most elegant approach to do this. So instead, what's by now widely used are quaternions, which I'm sure many of you have come across or heard of before. And exactly these problems of rotation matrices and these degree-based representations are what made them so popular. They've actually been around for surprisingly long time. A guy called Hamilton invented them in 1866. I think they're actually from Edinburgh, if I remember correctly. There's somewhere a plaque, if you visit, you can find in the city somewhere saying like this is where he had the bright idea back then. So yeah, a Scotsman. And back then, I think people weren't too amazed, because it's not so intuitive, as you'll see in a moment, and no one knew what to do with it. But not quite 100, but quite a while later, no, more than 100 years later, 85 of computer graphics, people knows, oh, this is actually neat if we use it to express rotations for computing. And the reason why it took so long, probably to pick this up, is that it's an extension of imaginary numbers. So I hope you remember complex numbers from school, at least some of you, right? So you have basically an extension of your irregular array of numbers with a second dimension, the imaginary part, and often written as real part A, it's imaginary part B. And there are special rules for working with this imaginary part. So, but it kind of spans a 2-dimensional plane already. Essentially, we're working with numbers along a line, but you can show also these complex numbers actually have some neat properties, especially for physics applications. And these quaternions now are an extension of that. So now instead of 1 imaginary part, we have 3. Typically written in something like the way down here. So you can imagine this as, again, a basis transformation. We have a real part, and then 3 vectors, I, j, and k, that span new directions. And in total, the real part plus these 3 imaginary ones gives us 1 quaternion, 1 vector, with the components being this S, X, Y, and Z, so 4 components put together in a vector. Now there are different ways to write this. Either explicitly as a vector with 4 numbers, or you can also think of it as a real part and a 3D imaginary vector, because actually later on we need the imaginary part. So in a way, this V here, that's actually the important one. Right. Essentially, you can think of it as a 4D vector with some special rules. The rules are also not super intuitive. Oh yeah, it's written out again, a real and imaginary. They're summarized here. I don't want to rederive why it needs to be exactly this, but for normal complex numbers, just as a reminder, you have I times I flipping being -1. Now for our 3 complex parts, we actually keep that along the diagonal. Every j times j or k times k is -1, but there are special rules, like I times j gives -k, or right, k times j gives I. So on first sight, it's really not clear why it's this way. I don't want to rederive why it's exactly this way, but if you set it up just like this, you can actually work with it. It gives you a proper system of numbers and values, proper space to work with. And luckily, you typically find these in a library. So also in the exercise, well, they're actually provided by DirectX typically. So usually you don't need to implement them, but it's good to keep in mind. This is what's behind it. And right, multiplying quaternions is actually not commutative. So if we have 2 q's, we have a q1, you basically multiply it. There are different ways to define this, say with a dot product, or if you do a full multiplication without this, we'll write it like this one. But for both of them, this is not equal to, just to explicitly have it, the multiplication the other way around. So it's like matrices. It's actually important how they're processed. And you can still kind of just think of it as 4D vectors. And whenever you multiply a certain component of one with another one, I need to take care that the corresponding entry might end up in a different spot. But in a way, it's mostly about carefully adhering to this table here and sticking to it. If you want to implement this, there's no magic behind it. But yeah, this work is also usually done for you. And now what turns out to be useful in our context are actually unit length quaternions. So unit length is important to, again, you can think of it as normal vectors in this 4D space. And they have a special form. So what we're interested in is for a certain axis n. So if we want to rotate around a certain axis, now specified as x, y, z think of it as in 3D space, by some angle phi, then the quaternion that does this has this form. So we have our angle phi, we have a real part, cosine of phi half, imaginary part scaled by sine of phi half, and then multiplied with this normal vector. And here you have the whole construction written out. So it's cosine times the sine times the normal value. And this is the quaternion we need. There's a question, yes? You're asking, so the multiplication table that we just had. So these are the rules, how to work with it. You're asking whether the quaternions numbers as defined with this table are an algebraic body. That's a good question. Probably, but you can look it up. So yeah. I don't have in mind the exact requirements for an algebraic body, but probably, yeah. Okay, yeah, no, out of my head. I also don't want to tell anything wrong here. That's a good point to look up. We want to work with these quaternions here and applying them now to a point P, which was our goal before, right? We have some point P, we want to rotate it. We actually also need to do this in a certain way. We have this quaternion Q, and you actually need to multiply it from both sides onto a quaternion where the real part is 0. That's why from before, in a way, the imaginary part is even more important. You basically construct a quaternion from P by saying 0 and P. That's what's written here in the center. So real part 0, and your previous 3D coordinates just make up the imaginary part. So typically, actually, the imaginary parts correspond in a way more closely to the 3D space you're working with. And then also for this Q tilde here, this is actually a conjugate, meaning we flip just with a minus sign these three imaginary parts. And then in between here and here, what's not written out, this is now a multiplication, but we're basically multiplying again from left to right, different quaternions here, and we need to make two multiplications, basically Q times this one, and then this times the conjugate of this quaternion. So that's not written out here, and I do have it on the slides, but in a way, right, this now follows from the table and the rules of working with these quaternions. So quite a few steps involved here. It looks fairly simple on paper. We're just multiplying three quaternions here. And this now gives us a rotated point P dash, again in the imaginary part of the resulting quaternion. I know it's a bit abstract, but the nice thing about this is that you can actually very nicely work with them. It's also, in a way, nicely modular. If you set up, right, rotate something around a certain angle in this way with the quaternions, that gives you a nice interface and algorithm to work with any orientations, consecutive orientations, and eventually with the orientations that we need for our rigid bodies. So, for example, what still holds nicely is you can combine two consecutive rotations as a single one, just like before. Just to give a few examples. So, right, you can express 2 as 1, or you can combine two quaternions into a single one. And the reason why I wrote out this one again is, so here we're basically dealing with multiplication first by some quaternion Q1. Here this conjugate is now written with a -1 actually. All right, so this was this triplet that we had before. This gives us a position rotated by Q1, and then we rotate it by Q2 with these outer two multiplications. We can combine this into a single one by taking, right, Q1 times Q2. But now we basically need to, right, we can think of this as a pre-processing step. This gives us some new quaternion. We apply one time the conjugate, and from the left in its original form, taken together, this again rotates by both. So you can work with them quite nicely. And the big advantage here is that now we're actually only dealing with 4 values, and they don't have these gimbal lock problems. So to recap a bit, I don't know, re-evaluating the different alternatives we had these Euler or fixed angles, which only require 3 variables, which is great, very minimal, and they're pretty simple. They're actually not unique, and they have this gimbal lock. So this is not nice, not so fatal, but this gimbal lock is really this is in a way a killer argument, right? Say this is a no-go, or if we can avoid it by any means, that's definitely good. We can actually show in math, in general for rotations, 3 values are not enough. We can actually prove this, but it's really a mathematical property. So we need more. We had these matrices, which are also nice to work with, can be concatenated. Actually typically fit into APIs quite well. They don't have this gimbal lock problem, so in a way, fundamental step forward, but in a way they're very wasteful. Instead of having too few, now we have too many. And because of this, they actually need some additional steps to keep it in check. And also not unique. This is actually, this is unfortunately not completely fixed by any of this, but in a way it's a step forward, but a bit wasteful, and hence that's why these quaternions are popular, and I think by now actually pretty much standard and widely used, because they're in a way the best compromise. So they're almost unique. I actually show from this construction of how they applied both the original one and the full inversion, a minus q, do the same thing. So at least only 2 solutions. It's relatively easy to go to a unique one in this with this distinction. It's not a whole space of solutions that you need to deal with. They don't have these locking problems. This is super important. And it's also pretty efficient to work with, to concatenate, for example. So they actually still require a normalization. So I've mentioned briefly, we need these unit length vectors. If you work with quaternions, you always update a quaternion basically by some delta to get a new one. It can still happen that they drift and don't stay unit length. So a bit like with normal vectors, you actually need to normalize them to have a length of 1. And admittedly, because of these 4 dimensions with 3 complex planes and these additional work rules, they're not super intuitive. You actually get used to this. If you use them more, you do get more intuition for it, but if you've never used them before, these numbers probably won't tell you anything if you look at the quaternion. Nonetheless, because of all these advantages, in a way, it's worth typically getting started with it. And it's also what we recommend for the exercise, actually, because this is really the way to go. It's very widely used these days. Because of that, a few recommendations working with quaternions in practice. So we probably don't want to start directly having to kind of if you set up a rigid body and it should be somewhere in space in a certain location, you don't want to directly have to enter a quaternion that puts your body in that position. So in practice, it's actually good to have conversions. You typically specify something like these Euler angles originally to set up your system, or with a matrix, and then convert it into a quaternion. So they are actually nice conversion functions that handle all the central work. So for the main simulation, we'll keep this. So that's important to keep in mind. Basically, the orientation of my rigid body in a simulator, also the one for the exercise, is a quaternion. So your rigid body will have a quaternion that basically says it's right here with this orientation at the moment. But once you have that, say if you want to display it on screen for transforming points in the triangle mesh that belongs to a rigid body, for example, it's good to have a rotation matrix again, and frameworks like DirectX actually have functions for that. Right. So also a few warnings about the data type here, because as mentioned before, we actually interested in the imaginary parts, these 3 additional components. Many frameworks also think of it as basically 4D vector with 3 imaginary parts and then an additional value. So this is a bit closer to the implementation, whereas mathematically you would say it's a real part plus 3 additional ones, but please be careful with this when converting back and forth. And right, the corresponding functions that you need are something along those lines from DirectX, but you can also find additional instructions there and examples in the exercise sheet. Yeah, and then maybe just to point out also on the slides, please don't learn these, but I do have the rules for calculating actual multiplications or so. Say this one here, right? If you need to work with these in the exam or so, we'll give you the basic equations. Please don't learn these. But just to show you once how it's constructed, so you basically have these 2 quaternions. You multiply the real parts, and then you have additional terms combining the imaginary parts. Again, we now need to go in and do the corresponding dot product and other multiplications or cross product operations. And from these, right, you get different combinations of the imaginary parts, I, J, JK, and so on. And then you need to basically map all the results back to your final vector that you want to get out here in the end. So, right, in a way, no magic, but you definitely need care when implementing these. Yeah, so with these quaternions now we have a tool for working with orientations in our simulator. Any questions about the setup here? Because if not, I think that's also a very good point for a quick break. And then equipped with the quaternions, we can get back to the rigid body simulations and put that to use to construct a 3D simulator. So let's continue in 5 minutes. All right, let's continue with 3D. Any questions about the orientation part? We'll get back to it in a moment. Yeah, so I've already mentioned, in a way, positions are the easy part. We had X and Y, now we have Z. Everything we had for the linear part still works, just with one additional number, basically. The challenge is with the orientations. So that's where we use quaternions, as just introduced. Instead of what we had in 2D before, basically single angle was fine there. Now we need a quaternion to work with. The angular velocity actually extends quite nicely. That basically was a reason why it's introduced as a vector, even though we could have worked with also some scalar quantity in 2D, but we still have a 3D vector denoting an axis and a rotation around that axis. Right, I hope you remember the vector we had before in 2D was basically this vector 0, 0 with some z component. It's also can recommend keeping in mind that it's basically a 3D quantity, even if we have a 2D simulation. Right, so the rest of the simulation is x, y, and 0. For the rotation, we have 0, 0, z. Well, that's how it goes together. And now in 3D, we just have three values for both. The length of that vector still tells us how quickly something is rotating, also just like before. Just that the first two now can have an entry. The inertia tensor also came up today. Now it's really a rank 2 tensor matrix. So yeah, tensors are actually this generalization. So theoretically, we could have even higher rank tensors. They actually do come in handy in certain situations. You can think of it right like this dense block of values in any number of dimensions, but goes a bit beyond what we deal with. So we just have this rank 2 quantity, which means we have something that looks like a matrix. The way it's constructed is also basically still the same, just now for the 3 dimensions. And we basically dealt with the diagonal part of this before for 2D. So one way to think about it is that we have an outer product of these position vectors, the x, before we had I, now we have an n here, so we're summing over n. Where before we had a dot product, we now have an outer product that creates a matrix, and we weight it by the mass associated with that point. And so we do this we sum this up for all the points we have, and then we did a bit too much. What we need to subtract again are the diagonal components. So the diagonal of the matrix you get out here has 3 entries to be denoted by matrix A, A11, A22, A33. Aesthetically, that's the trace of the matrix, and that these values we actually subtract. Or it's actually 1 minus this original matrix. So it's closely related. I don't want to go through the details why it's exactly in this way. Basically also comes from rotating the different quantities by certain angles around the center of mass of your rigid body. But if you're interested, there are materials that show that this actually does give the right answer. And this X transpose is really an outer product, so it gives a matrix. And the resulting one, general form, is summarized down here. So, warning, there's no more n here because this would make the whole equation a bit longer. So all these x's are components of every single point that you might have in a triangle measure. So these are the terms you get out in a way, I don't want to spend too much time here, but if you, the use case is basically if you're really just given a point collection like a triangle mesh, you want to use it in a rigid body simulator. One good approach is to say, well, my mass, the mass of my body is actually at these vertices, and then you distribute the mass and compute this inertia tensor for it. That's only for the general case of really some, well, you rarely have a point cloud. Typically it's a triangle mesh, could also be a point cloud, some sampled location. If you're given something like the box for the rigid body exercise, there are actually many primitives, spheres of course, but also capsules and ellipsoids and so on. They're actually closed form solutions because the equation on the previous slide is again the discrete form of an integral. Normally you would think of this as a continuous material, right? A real object also you don't have individual points, but we think of this from a human perspective as something that continuously changes. Then you'd have an integral quantity, and if you work this out, what you actually get for many simple objects are fairly simple expressions. Here's the one for a box. So here we have a box of W, H, and D, width, height, depth. And then you basically get, interesting, a lot of the off-diagonal terms cancel out for many symmetric objects. And you're left with terms, for example, for X, that deal with the other two. So the height and depth in this case. And like for Y, you get W and H scaled by 1/12 of the total mass. And one good question to think about is, well, if I now set up, or for in the exercise, if I would take this box and apply the previous equation with all the corner points and compute this in comparison, would I get out the same value? Any thoughts? Should it be the same if I just apply the equation from the previous slide to the corner points and compare it with this one? Because it's actually not the case. People have tried this in the past in the exercise, say, well, we computed this with the other equation and suddenly we're getting different, or we're getting different inertia tensor than from the one we would get from this one. The difference is exactly this integral viewpoint. This is exact. This is really treating the whole object along those dimensions as a dense block, whereas in the other point, you're locating all the mass in these infinitely small points at the corners. So it's really different mass distribution. It should be different. With the previous slide and the vertices, you basically get nothing everywhere, and then just in the corners, all the mass. Whereas here, you get something that's really filled. Your whole box is filled with the material all the way. And in a way, this is a more correct answer. So if you can use these analytic solutions, it's also recommended. In practice, right, you do either this or a step like this one or the vertex-based step if you don't have any closed form solution for an arbitrary triangle mesh. And from that, you get this 3x3 inertia tensor for your simulator. So the inertia tensor is typically computed in the rest state, right? So you're getting the object, you're defining it somehow. You need to compute the center of mass and how it's shaped around that center of mass. So there's a certain rest state for your body, and computing it, right, can actually take a bit of time. So you don't want to redo this in every step. And hence it's a good idea to, in practice, also just update the inertia tensor with the rotation. So the inertia tensor needs to change because it really tells you that around the center of mass, where are the pieces of mass? How are they oriented? So it depends on how your rigid body as a whole is currently oriented. And right, you can basically treat it like so often with orientations and rotations, like a coordinate system transform. So if we can imagine we have a quantity from the right side here being applied, that should be rescaled by the inertia tensor. You basically first undo the orientation, right? So you basically map your body back to its initial state, then apply the weighting by the inertia tensor, some mass weighting, and then you rotate back with this matrix. Right. This is a common form you have for coordinate transformations. You have undo it, work in this space, and then redo it. Sounds a bit wasteful, but it's correct, and right, there's actually no simpler way of applying it. Other ways of formulating this update multiplication with a matrix would be equivalent. So, yeah. What we later on need is actually typically the inverse. So we usually need this inertia tensor to -1, which effectively for matrix denotes something like 1 over. There's one exception for the setup phase. We typically think about specifying a normal angular velocity, right, in terms of some direction and how fast it's spinning, or offset 0. But if you want to prescribe something spinning around x directly, you might want to set this w, and then you actually do need to multiply with the normal inertia tensor to compute the angular momentum. But for a simulation, that's typically the only bit where we really need the normal inertia tensor. Later on, we're always dividing. Yeah. And this whole transformation likewise holds for the inverse. So it doesn't matter whether we have I here or I inverse. The same concept later on for dividing by the mass. Yeah. So now we're basically building step by step the different pieces that we need for the 3D simulator. One point that I already mentioned before that I now want to re-emphasize, mentioned this last week, basically in 3D, things aren't so simple anymore, unfortunately. So we can't do these simple Euler steps. The reason is that, unfortunately, the quantity that stays constant without external influences turns out not to be the velocity, but it's the angular momentum. Or in general, actually the momentum is what stays conserved. The velocity can change. The linear one actually doesn't if you have no forces. If we don't have forces and something, right, if we were in space and I would shoot off this object, it would just keep flying in a straight line. That doesn't happen for the rotations. So it's really not intuitive, but if I have an object that's spinning somehow, it's rotating, and even if there are no forces, this axis of rotation, the W, can change. So we can actually also analyze this in terms of the eigenmodes or the eigen values and eigenvectors of the dynamics of these rotational motions. You can show that if you have something that is not symmetric around the axis of rotation, then it basically gets redistributed along the primary axis. Definitely not intuitive, but there's a nice way to show this, namely in space. If you try this out in space, you don't have any other forces, and you start letting something spin, then you actually see this effect. So I found a nice video from the space station that shows this. And here now, astronaut does exactly this experiment with a book, spinning it around different axes. And these are the stable ones. So here, this book keeps on spinning. The other one, this one, the center is also stable. But now we next flip around the long, start spinning around the long axis, then observe what happens. Oh, that's a short one. Sorry, it's a short axis. So I hope you could see, right? It was basically spinning around the center axis of this book. And the book, although initially it really just spins forward, it starts redistributing this motion to the other two axes and then goes into this tumbling motion. So it's really not intuitive. There's not something you could easily predict how this happens, but it's really, it does happen. This is really a real experiment. This is how the physics behave on our planet. Most like all other similar 3D planets as well. So this is what we also need to capture in a simulator. And what we need to take away from this is that we need to actually work with a conserved quantity, the momentum. Because the L, this is actually what stays the same. So this is what we can keep and advance forward over time steps. We should not look at the velocity directly. I already basically hinted at this before, but now it really, I hope this video shows this is how it should be and what we need to do in 3D. Right, so we actually need the current inertia tensor to properly compute this. And then what we can do is compute it with the equation from before. Compute the torque. We have some force that will just map from world space into a rigid body based on the local positions that we get. Then we can apply this force as a change to the angular momentum, the L, with an Euler step, for example. And from that new L that we get, we basically convert this into a angular velocity W by dividing by the inertia tensor, multiplying with the inverse, and that gives us the actual W. That is the quantity, and give it a try if you have an object like this book actually spinning around, let's say, the slim axis. You should, in your implementation, also without any forces, see that this turns from a constant angular momentum, or one that doesn't change over time, into different axes of rotation in the W. But now, in contrast to the velocity, the important change is that this W is really a derived quantity. We just recompute it and overwrite it from the L. So this is not something that carries over to the next time step. It's never directly updated or changed. It's just something we get from the L. But yeah, knowing this, this is what we basically need to do because of how these 3D dynamics work. If you follow it, then it gives you the correct answer. Right, this is the process summarized again. We start with the forces, make an Euler step for our angular momentum, now probably written out in terms of also a time value. So this is now the new angular momentum. We actually do need the updated inertia tensor, but so far, right, our orientation has actually not changed. So right, this is just in a way the previous R, although there's no explicit time step. And then with this step, we compute the angular velocity at the new time step. And okay, let's fill this in. So for 3D rigid bodies, we now have, looking at this picture from before, these steps to update the angular velocity. There's still one part that we have left out, namely the orientation, right? This is the motion, the velocity of the rotation. We still need to update the actual state, and this is where the quaternions come in. So we now actually have this orientation, we call it R, that we need to update over time, and this R now is a quaternion. And this is actually a point that I have not described so far. So if we have something like a position and we want to update it over time, right? So for the positions, we just had a certain vector and then we could add an offset to it. Now we have this quaternion. How do we actually update the quaternion to get, right, basically an integrated quantity, something that changes over time by a given delta? The answer is the following. We can show that the time derivative of a quaternion R is actually given by a step, our angular velocity, formulated in terms of this quaternion multiplied with R and then 1/2. And in practice, this is just the delta. So to make a full Euler step, this is the equation you need. You have an old orientation, and then do a step by size h for a time step, and this is the derivative. So 1/2 times w times r, and this gives you the change of your original orientation, and with that you get a new r that contains the orientation, in this case for the next time step. Yeah, so right, some notes on a rotation matrix. So you can actually express a cross product as a rotation matrix. So in this case, if you actually want to apply a motion by some angular velocity, or w, in terms of this cross product to the rotation, this is actually quite neat. This would have been an advantage if I would recommend rotation matrices to express the orientation, which I do not. But kind of as a side note, there are actually some also positive aspects to using this, potentially why they were used before. So our somewhat unintuitive delta of the quaternion from before becomes this fairly nice expression. So this is essentially a cross product, if you look at these terms. So this is very nice, but rotation matrices are not recommended. So I hope you don't need this, but it's nonetheless still good to point out there are also some positive aspects about this nonetheless. Yeah, but with that we can really come back to our whole simulation algorithm in 3D. Now we really have all the pieces together. So our pre-computation stage is basically the same as before. I now just wrote out the full expressions like the I here for 3D. But we're basically just taking, this assumes we have something like a triangle mesh, so you don't need this for the boxes of the exercise. But if you had a triangle mesh, you actually would need to compute the center of mass, your offset positions, and the inertia tensor. Then you need to set up the state of your rigid body. So this is where we now really need the first inertia tensor in our example. We actually start by specifying L, so we don't even need the multiplication by the inertia tensor. You could imagine also here starting with the W and then from that computing the L here. But okay, right, these are all pre-computation steps. It's relatively straightforward. The main simulation algorithm, the force part stays exactly the same as before. Also for the linear center of mass motion, it says before, the change only happens when we start to deal with the angular components. So now for the orientation R, we have this quaternion update. So keep in mind this R, although it's not visible here, didn't want to introduce another symbol or variant for the quaternions, but this is a quaternion vector and needs to be treated as one, so we can't just add the W on top of it, but need to write out this expression. And keep in mind that in between here, this product is a quaternion product, so from the previous slides, does more than a simple multiplication, but something that is typically handled by direct X or so. And for the angular momentum, we have the steps introduced as before. Angular momentum itself is actually surprisingly simple with the Euler step because that's a conserved quantity, but from it we then need to compute the actual angular velocity, the W. And with that we have everything together. We can, for example, show this on screen, computing the transformed world space positions, or we can compute the velocities as well. This, right, again, in a way, doesn't hurt to have for all points. Potentially you would only need it, say, if a point is colliding. You could do this on the spot, but right, this should just illustrate, once we're done here with our simulator, we can basically compute all the world quantities we need for showing something or for doing other steps. And then again, we repeat the step. Any questions? Right, in a way, this is now just putting the pieces together that we had in the previous chapters. Also one more note. Oh yeah, one good question here that potentially comes up when you look into this, that came up in previous years, but I think it's worth thinking about right away, is for my spring systems, I was writing this wave so much about better integrators and so on, and suddenly here this is all about Euler steps. So an obvious question is, well, or you could ask, well, you told us Euler steps are so primitive and not good, why don't you do something better here? And it's interesting to think about. So why don't we use, for example, Leapfrog or Romikuta or some higher order integrator to do things better, to get improved dynamics out of our rigid body integration? So one aspect here for Leapfrog is that if we integrate this forward, if you imagine what basically happens in a time step, the forces we have, or that we had in the mass spring system, which were driving everything, right? These internal changes of our deformable bodies, those don't actually change here. Our bodies stay fixed. And the only forces we have are maybe gravity or some user interactions. And assuming that these user interactions are not super complex and changing very quickly, for the velocity, this is actually constant. So we still have a second order ODE, right? We need to integrate position and velocity, but the changes of our second variable, the velocity, are actually constant. So you can imagine this basically over time being like a step function, right? We have steps and forces, and then maybe another force, but for every time step of size h, this is basically a constant value. And if it's constant, then these higher order integrators actually don't give you anything. Then you get exactly the same answer, because the additional information that we got from the higher order integrators is basically by looking at what happened in between the steps. What changes do we have? That's true for the forces. The collisions, of course, might change, right? You might have collisions in between the time step, especially if you have fast objects and so on. The bad news there is that the collisions are typically very geometric, so kind of finding out where my objects collide exactly, how they collide on corners and so on is expensive computationally. And if I would want to resolve collisions with a higher order integrator, I basically need to handle the whole collision part multiple times. Right, so if I would do something like Runge-Kutta 4, I would really need to recompute collisions 4 times to see how, for these intermediate steps, would have my object collided for these hypothetical steps which I don't use in the end. And that's unfortunately expensive. So that unfortunately does not pay off. Or you would handle this differently. So for really accurate collisions with fast-moving objects, there are basically other ways to handle this more efficiently that I want to come back to later on. But the cost of handling collisions in arbitrary settings is typically what means that it's not attractive to do these additional steps. So hence, we're stuck with Euler steps for rigid bodies. But nonetheless, in other cases, they might be useful also for rigid bodies. We can actually do more, but these two are basically the answer. The forces are constant per time step, and collisions are expensive because of that. In practice, Euler steps or potentially smaller Euler steps are actually a good idea in 3 dimensions. The impulses I introduced before, it's summarized again here. We had, this is the equation I had on the slides before, the full one now with all these rotational terms. And the somewhat new bit is we, of course, also need to update now our angular momenta, the L values for A and B, but the impulses work like a torque with plus and minus again like before. So there's no fundamental change here. This carries over pretty nicely to 3D. Yeah. And again, if you have something fixed, in 3D, you would also basically remove it from your simulator, effectively saying, well, the mass is infinite, which means that all these terms, this still holds for 3D, with an inverse would drop to 0. So you can basically leave them out and only treat the body that is not fixed. Yeah, because once the simulation is running, we actually, for masses, always need the inverse values. Yeah, with that, we really have all the steps for a full 3D rigid body simulator. And feel free to think about it a bit and get started with the exercise. I think it's up now and definitely a good way to get into these topics. So we can, of course, also discuss questions next week in more detail. I do want to use this chance to show some video examples. Not these. Okay, now it's okay. So this is from Blender with Bullet, and in a way it's really just a rigid body simulator. But the nice thing here is now we have a lot of rigid bodies. And I think these videos are a nice outlook. There are some more parts here with contact and some coupling, but most of the dynamics you see here are really plain 3D rigid bodies, and I think a lot of the interesting bits we're seeing here are just coming from scaling that up. And the nice thing, the motivation for having 3D rigid bodies is really we can do it fast. It saves us a lot of work. And these are some nice examples what you can get out there. So I think this one is especially nice. There are other examples, but this is more than 30,000 just boxes, rigid body boxes. And right, this gives some interesting behavior. I think this did come with some replays. So in a way, I think these videos are nice proof that dealing with the additional complexity of the rotations does pay off. Right? This I think you could not really simulate with mass spring systems. And the interactions you see here, especially this free flying, are quite nice to see and complex. This we cannot handle yet, I have to admit. So for stacking and these piles of objects on the floor, we need extensions. So friction and stacks are not yet supported. Please don't try it in the exercises, would not properly work yet. We'll get back to that. But in a way, I think a large part of what's happening here we have captured with our simulator now. Right, but I think that's a good point to close here. Feel free to get started with this, and then more next week. Or one more time. See you next week.